Hello, everyone. Welcome to this workshop. Today we have Radhakrishna Sanka, or Krishna, present to you a workshop on 3DUF, which is a microfluidics platform. And so Krishna is a fifth-year PhD student at Douglas Densmore's lab at CIDR Lab, which is at Boston University. And I think you're also working on a spin-off, a little company on this, right?
Yeah, I am actually.
Yeah. And then outside of that, you're also active in the kind of biology and DIY bio community, and as well a new community called Distributed Diagnostics, where I'm also involved with, and we're trying to kind of gather everyone who is interested in developing new open source tools related to microfluidics and making it easier to fabricate and source tools and source knowledge around microfluidics. So I'm going to hand it over to you, Krishna. I'm going to hang around here. If anything's going wrong or you need assistance, just let me know. Okay.
Yeah, thanks a lot, Kenza. So let me fire up my PowerPoint. So can you all see it in presentation mode? Okay. So welcome, everybody. I'm super excited to talk about 3DUF. And, you know, as the title kind of indicates, the goal of this entire talk is to figure out, is to teach you all, you know, how to extend 3DUF for either, you know, any kind of a fun project, or if you're actually using it for one of your publications, how you can actually use the open source code 3DUF provides free of charge and extend your own research onto it. Yeah, so I have so the way we'll kind of split up this workshop is I have a small slide deck, about 15 slides, where I'll just go over and talk about a couple of design philosophies and everything that go behind 3DUF, about why we built 3DUF the way we did and why it's kind of different from like AutoCAD and everything. Since this is like a workshop and formal setting, I would love to have a lot of questions and feedback. And, you know, there'll be a section where I'll be writing some code and demonstrating how you can actually add new components to 3DUF, how you can add new UI features, and how to go about doing all these things in a very easy way. And also talking about like some of the other libraries I have around 3DUF, which you can use for like post-processing the designs you have created on 3DUF and doing more computational or algorithmic research on them. So as most of you know, like microfluidics and lab on a chip is something we're all familiar with in the space of synthetic biology or design automation or bioautomation. The three main reasons when we think about like why we would want to use microfluidics is because you could get like really, really high throughput. The examples on the right are example devices from like droplet microfluidics. The top one is doing pico injection, where you inject a small amount of reagent, picoliter volume of reagent into a droplet. The middle one is where two different droplets, that means you could have two different samples are getting merged one after the other. And the third one is where you're actually selecting between two different droplets. As you can notice in the video, the ones which are flowing on the top column are dark droplets, and the ones which are going at the bottom are the light ones. Now, one of the most interesting things about doing like these kind of droplet things is that droplet-based devices is that you could actually process like 1,000 samples a second. And these videos which you're looking at over here are actually slowed down by 200 times, 400 times. And that is something insane, because instead of actually doing like, you know, one experiment at a time where you're pipetting each and every test tube, each and every pipette, you can actually mass produce and process all these samples in a large scale setting. While these are examples of super high throughput devices, there are other kinds of devices which are also popular. And ever since like for the last 20 years, academics and researchers have been like building all kinds of crazy devices with super complex features and densities and valving and control and operational capabilities over there. This is basically my greatest hits of microfluidics kind of poster, where we talk about how dense can we make the microfluidics, and why we need like design tools which are specifically designed for making microfluidics. But the big thing that you'll notice is when you go into like a bio lab, right? And even though like all these people have been building these devices, you don't see them very often. They're almost always one-off devices. And if you think about it, right, like this is how, if you only had those devices, this is how your average wet lab would look like. This is like a picture of a data center, but you can imagine each one of these racks to have like microfluidic devices. You just slide in, and samples are going in and out automatically, and you're basically doing science at the like millions of samples a second scale. But the reality is your average lab kind of looks like this, right? You have a bunch of equipment lying around. You have like test tubes, pipettes, random beakers and flasks and everything floating around, and it's nothing in the sense of like an automated miniaturized system. So the big problem about what happened from all those publications to what was actually going on over here is that the first issue was that first problem was that you need like multidisciplinary expertise to make any idea you have into a real device. The second part of the problem is that the supply chain is super fractured. It's non-trivial to actually source all the components, the materials, the substrates, the adhesives to put things together, and it's not simple. In most microfluidic labs, which you see in academia, there is like knowledge which is transferred from like one postdoc to a grad student to another grad student to an undergrad and whatnot, right? And even in our lab, where we stress a lot on like automating the process, the details of the manufacturing process, what exact parts are there, are hard to keep track of, and it's hard to hold on to everything and make it easy to replicate these device designs. So the answer for most of these problems is that, like in terms of when you have like multidisciplinary expertise, what you kind of need to do is you need to insert design automation. So the best examples of design automation are in like the VLSI, like the IC, semiconductor IC world, where people design thousands of gates and transistors over there, and they do most of it automatically. They write a high-level description of what it's supposed to do, and then they synthesize the entire design. The second aspect is that if you want to address the whole fractured supply chain part, you got to really say, okay, we're going to make everything we do open source, like all the design files which we have, all the part lists which we have, all the code which is going and running these devices. And you got to make them all maker-friendly, because otherwise nobody else might be able to get it. For example, some scientific suppliers might not ship their components like across the world. If somebody in India, like where I'm from, wants to do it, they might not be able to get the thing. So the solutions are always making things more maker-friendly and making them more open source, because that way you use more standardized parts. It's cheaper and easier to replicate these things. And hence, like both of these things put together means that you need like an open ecosystem. And that's kind of where 3Duff and a lot of my research actually comes in. So this is a quick screenshot of like going from like idea to design of an entire microfluidic device. This is sped up, obviously, but it took me a grand total of 20 minutes to make this entire device design. And if you were doing this in something like AutoCAD or something else, or SolidWorks, it would probably take you 2-3 hours at the very least. I mean, we have some folks on the workshop here who are probably experienced in making these designs. So I'd love to hear more about, like what your experiences have been in like designing devices. But the most important part, as you can see, is that the way we design this entire device using, this is a screenshot of 3Duff, right? So the way we design everything in this in 3Duff is that we think about everything to be parametric. We think about everything to be standardized components. And we put together standardized components in parametric manner with parameters, which we know how to modulate, and we know how they will behave at the end of the day when we modulate those parameters. And that means that you can actually standardize the entire device design, and there's a lot of benefits that kind of come in. And it's not just the case that using these components, using the standardization is helpful, but the thing is, our lab at SciDar thinks about like tool chains, right? Like we think about what can we do. And 3DAF you see over here is just one of the tools which we have for like CAD tools. We have standards which are underlying all these CAD tools. We have languages which will let designers and more computer science savvy designers design the entire device without actually drawing anything on the canvas. And we have tool chains which are actually stitch together all these different pieces together and generate the final design and figure out how to do the manufacturing for them. So in this talk, we'll be mostly talking about how we can extend 3DAF, which is an open source platform for interactively designing microfluidic devices. We'll be talking a little about Parchment. If time permits, I'll be showing you an example of how we can design a device in 3DAF and how we can use the Python libraries which we built to open those designs. And finally, we'll be talking a little about Mint, because the languages and the standards we've been introducing throughout our toolchain and everything is something we use everywhere. It's a way we use to standardize everything. And we show that, like how the thinking goes from like high level design to like all kinds of design automation pieces, and how we how 3DAF kind of stitches all of that together under a single easy to use interface. So before we kind of dive into this part where, like talking about more about microfluidics, I'm just going to take a look at the different chats we have. It seems like we have a couple of questions. Yeah. So the first question is from Alexis. Is anybody doing that, like the microfluidic stacks? Yes. So there are companies, I am blanking out on the name at this point, but there are companies which are making more culture devices and CRISPR-based things, more application-specific devices, but they do build them in forms of like racks and standardized, maybe like bioreactor volumes, like mini 500 ml reactor volumes, maybe not in terms of like microfluidic volume sizes, and that's what is there. Then very tidy lab. Yeah, I guess that was basically a little photo opt over there. So let's kind of dive into like, like what is a microfluidic device and how do we need to think about that? I'd love to know if, if there's like a show of hands or something for folks, who've already built microfluidics and whatnot. It'll be good to know if some of you have already built something. Are there standards to connect? Okay, there are a bunch of questions. I will answer them. Okay, and on the research end, are there microfluidic machines or racks that can replace manual plate experiments, or do? No, on the research end, I don't think there are anything, but there are a lot of companies out there right now. So there are all kinds of projects going on. And in fact, one of the things we want to do in the distributed diagnostics community is to build these replacement for like manual plate experiments. And we'd love to hear more in terms of like what kind of applications do you want to automate, and what is it that you want to do, like induce, shake, measure, load, right? Like, but are there more specific things that you want to work over there? What do you want to load? What do you want to unload, and whatnot? That'll be great to hear from you. And are there standards to connect devices? If you're talking about physically connecting them, there is a work group based out of Europe right now called the Microfluidics Consortium, which is putting together standards for like how to make interconnects between devices. The thing is that, for the most part, this industry has been like a very bespoke science application kind of a industry. So everybody kept doing their own thing. And now the consortium is trying to pull together some standards to say that, okay, we're going to get some ISO certification for these things. If you build these standard connectors, there's some standard testing mechanisms. And so it's slowly building up. But if we have more academia and DIY contributors in this space, it can really speed up the work, because it increases the number of people actually testing these things out and seeing what works and what doesn't work. I'm happy to chat about these things if you're interested, and make the connections to the corresponding standard scenes. So a simplified microfluidic device at the most easy level is that it's basically an assembly of like 2-3 different pieces, right? 2-3 substrates. The first thing, what I use throughout this entire workshop and in 3DAF, the color code we use is whatever's in blue color, all the geometries you see in blue color is what we call the flow layer. The flow layer is where, your actual science or your actual protocol, or your assays, which you're executing is actually happening. And the control layer is essentially the little pneumatic infrastructure which you use to control how the fluids flow in the flow layer. Hope that makes sense. I'm happy to elaborate a little more on that if you need. The second thing what we do is, now that we know what these flow layer and control layers are, one more level if we look down is that what we divide in 3DOF and everything, and how we standardize and think about designs, is that we break down the either the flow or control layer geometries into what we call components, which you can see are like the functional units where something will happen. This is just a representative design, but look, those are specific things what are happening, and whatever they're connected by are what we call connections. So the lines which connect from one component to the other are what we call connections. So taking that example from there, this is how we would basically describe the entire device design in 3DOF. We say, okay, here are the list of components which are there. Here are the list of layers which are there, and here are the list of connections which describe which different components are being connected one to the other. And by just describing all these things like a graph with some layer information, we can actually capture the entire complexity of a design very, very easily. So the reason why storing the design like this is superior to like how you do it in AutoCAD or SolidWorks is because now we actually know what functional components are connected to each other. Like, for example, in this example over here, the little round things you see over here, if you can see my pointer, the little round thing is what we call a port, where you put in a fluid input. And this other round thing over here, see, this little half moon structures is what we call a valve, which controls whether or not the fluid flows. And this serpentine looking channel is what we call the mixer. So let's say we wanted to know what happens to the fluid which is being injected from this starting port. We can, because we treat this like a graph of components and connections, we actually know how every component is connected to each other based on what the valve state is, how the fluid will flow through. And that is something you can't figure out using AutoCAD. And so when you're trying to build, constitutively build like large designs, having this ability to do that is going to make life a lot easier when you want to design large systems. What AutoCAD and 3DOF do, and they do it really well, is they let you draw a lot of different things. But over here, it's not about drawing, but actually describing what a system is, telling what the parameters and what the functional pieces are. And then, because it directly translates into a geometry, we can generate the geometry. And that's what 3DOF's entire philosophy is. Now, the second reason why components are useful is that, one, as I mentioned earlier, it allows for automation. The second is that we can actually make the manufacturing agnostic. So if you look at what, some of the reasons why those very complex devices I had at the beginning never really make it into the lab is because they're super hard to manufacture. And it's not easy to figure out how to manufacture those things. But by having our system and in the entire space of microfluidics in the literature between industry and academia, there's like a new way of manufacturing these devices almost every other year, whether it's CNC milling or laser cutting or photolithography, which are different manufacturing methods. It changes how one designs the entire device or how you prepare the final designs for manufacturing. And that is a really hard, that is a really annoying job. And so anyone who's designed like large devices will kind of attest to that. And because almost every design, every application might need a different type of a manufacturing process, the need for having by having these components, we can actually translate between different manufacturing processes. And that's what 3DOF lets you do. Right now, 3DOF's, the online version of 3DOF lets you manufacture using CNC milling and laser cutting and translates devices between both of them. Of course, there's a limitation on the kinds of manufacturing processes we enable right now, but it's something we can easily increase. And if you all become part of the larger 3DOF open source community, it's something you all can also contribute to make happen. So the second piece of why components are useful is because we can actually parameterize all of them. So when you're trying to figure out, like what exact geometry of the microfluidic will work, having all these geometries being automatically parameterized and easily manipulatable means that you can quickly have variations of a single design and check what is working best for you. In a lot of cases, simulations are not sufficient to figure out how exactly the fluids would behave. And especially in those cases, having the ability to like parametrically vary these geometries is going to make a lot of difference in your design and prototyping timelines. So it's not just one of them. Every component we have inside 3DUF and every predefined component we have in 3DUF is a parametric geometry, which means that you can actually vary all kinds of things in these geometries and figure out how they're generated. And the other thing is that because they're all parametric, it means that we can use algorithms to procedurally generate them. For example, for anyone who's drawn trees in like AutoCAD, they will probably know how painful it is. I've tried doing it and I gave up after like the first 10 minutes. So the one you see on the left is where, you know, a single channel breaks out into 4 different channels, right? Like a tree. That is kind of okay to do. But when you start making like the next version of it, yeah, you can copy paste some of it and make some connections. But then as it keeps getting bigger and bigger, it becomes really hard to do that manually. And like the one we have on the right is about, I think it's 64. And that is non-trivial. And let's say you want to change the channel width of this one, it's not going to be easy. But because everything we have is parametric and procedurally generated, we can easily modify this and it's super fast to do the changes. And as I was talking before, like we can actually make sure that we can actually check to see, you know, if a given set of components can be manufactured with any given type of a manufacturing process. And that's something we've built in to some extent into 3DUF, and we plan to extend a lot more in the future. I see a question. L systems for UF design. Can you say, Alexis, do you want to just unmute and ask what that is?
No, I was just looking at, because you were talking about like everything is parametric in 3DUF.
Yeah.
And you started showing some trees, and that just reminded me of the Lindenmayer systems, which is it's like a formal grammar to describe like branching rules, and it's actually been used in like 3D packages to model like real trees, but with like 3D geometry. So it's like branching and doing all those things by grammar rules. And I just thought about that. It was just little.
No, that is actually amazing. I'd love to chat about that more at some point. I'm actually putting together a grammar as part of my PhD process to capture the different types of microfluidic architectures and how connections and control will work for them. I'd love to chat with you on L systems at some point in time. It's fascinating to know. It's always fascinating to know more things which are going on. So now we actually come to the actual programming part. So before we get started on the programming, I want to know. So before we get started on the programming, there are a bunch of you online. So I just like to know a show of hands of how many of you will be actually writing code alongside me to make the designs. Okay, Alex says he'll have a go. Then anyone else? Because if you, so yeah. So what I'm going to do right now is I'm going to give you guys a quick overview of, you know, how to set up your little, the environment, what installations you need to do and whatnot. And I'll be going over like the design process of how to add like a new component into the 3DUF library. It's going to be a very simple component. It's not going to be super crazy, but I will be showing you like the different steps in which about how one goes about designing different components and how to go about doing it. So if you go to the Slack, there will be a link for like the for all of you who want to play around with 3DUF in the future. Go to the workshop channel, which is workshop for DIY Microfluidics CAD, and you will find a link in the bookmarks for like the installation wiki. I'm going to share the page right now, share my screen right now with the page. So this is the link. If you click on the link, it'll get you here. And this is essentially all the things which we recommend in terms of like what your recommended IDE is, what kind of plugins you want to have for development, for Chrome development and everything, and what package manager we want you to install for working on the JavaScript code. And for this particular workshop, we'll be working in compiling version 2, and we'll be basically extending version 2 and playing around with version 2. Because that's our new, it's our more easy, more open source accessible version, which we want people to mess around with and add more features to in the future. So the other thing is that if you clone the project, so what you should be doing first is, if you want to work on this, first make a fork of the project. And in my case, I apparently have the clone already. So what I'm going to do is I'm just going to go to my clone. I'm just going to fetch the upstream. I'm going to switch to the, actually, let me just delete this and I will do this again. So Alex, are you going and cloning the repository? I mean, forking the repository? Yep. What you should do is you should fork into it, because that way, in case you make any changes and you want to push it back, and you'll be able to do it. So we've had some more folks join in. I was just talking about forking the repository and stuff. I will show that from scratch right now. Like, I will fork it live and I'll show you how that goes about. So if you're somebody who is planning to like work on 3DUF and you want to extend it, first go to the repository. Then go hit fork. You can pick on any of your things. Now, once you fork the repository, it'll probably take like a couple of seconds for doing that. And so what you want to do at this point is you want to clone it onto your console. So in order to do this, let me share my screen. Sorry about that. I was just trying to, I accidentally closed everything. Okay. So now I'm just going to clone the repository, git clone. So I ended up cloning this repository here. So we recommend using Visual Studio Code as a thing, as your default IDE, because we picked out a lot of recommended plugins for this entire project, and that's the easiest way for you to work. Because if you look at the recommended things over here, everything from like Markdown to like all the other stuff will be popping up for you as soon as you open it. We set up a lot of things so that it's easy for you to like work in the Visual Studio Code. Now, the first thing you want to do is, I see another message over there. You should follow the V2 instructions. Yes. Thanks, Kenza. So as I said earlier, let's just follow the V2 instructions here. Then you go here. Basically, it's nothing but npm install. I have all the other things installed, so it should be fairly simple. But first, I need to like switch to the right branch, right? Git checkout. Webpack build. And then I'm gonna hit npm install. So it's gonna install all the infrastructure, all the JavaScript libraries and everything that it needs for you to run this. So any trouble so far, or are all of you able to keep on with what's going on right now? Okay, nothing yet. So I'm gonna stop the share and just share the VS Code thing so I can move around a little. And everyone is, feel free to chat. I want this workshop to be as interactive as possible. I know some of you probably are, like, because everything is remote, it's easier to not talk and everything, and that's totally fine. But if you have questions, feel free to unmute yourself and make comments or ask questions. It's always more exciting to just talk to people. I'm curious to know, like, what, I guess a question could be like, if all of you, what OSs do you all use for your software development, or what do you plan on using in case you want to use 3DEF in the future? Like, is it Mac, Linux, or Windows? Aaron says Mac. Then sometimes you can too. Yes. Yeah. I'm curious to know more about like how the Windows 10 folks are having this experience, because for the most part, I have some undergrads who worked with me who worked on Windows, and it seems to have worked fine. But I'm always curious to know if anybody has any challenges or if something's not installing. Okay. Now, basically, the entire bundle got installed and it's ready to go. So in order to actually build and show the live server version of it, now let me share the whole screen, because in order to show the live screen version of it, I'm going to do like npm run view serve. So this particular command you have will activate it will basically compile the entire project and then open up a local dev server, which you can open on the browser. I'm going to take a look at the questions. Some folks are talking about, yeah. I mean, for the most part, if somebody are looking at getting like the new MacBooks with the ARM chips, I think you should have no issues, because everything in this is built with JavaScript, and JavaScript has been fairly decent about like figuring out, like the whole npm system has been pretty good about like making sure that you can use it on a Mac and whatnot. Some of the other projects might not be that much more amenable for using on like an ARM processor, because some libraries and dependencies don't have any binaries that work in ARM. And so maybe in those cases, you might want to use some of like, an x86 processor. But for the most part, all the JavaScript stuff should work without any hassle. I'm always curious to know if somebody runs into any problems and figure out how we can help you.
Actually, Krishna, while this is installing,
yeah,
maybe you already covered this in the introduction, but I'm just kind of curious. So what can you expect, or what can you do differently if you're running this locally? As in, like, how easy or difficult is it to customize the code to do something ad hoc, or create your own workflows as opposed to using your online 3D tool?
Yeah, and it's actually super simple. And in fact, we have a process of making sure that in case you make a contribution and you want to make sure that whatever you have is going into the pipeline, we have a mechanism for actually vetting everything. We have, and of course, I have all kinds of crazy things going on in the background. But yeah, we have mechanisms for making sure that all the things are coming in, and it's super easy. You don't need to have anything loaded online. So it's basically giving me some errors over here, which we can fix without any hassle by just running a lint function. Okay. So by just running that, I quickly fix all the linting errors. Yeah, but it is super easy. Like, you don't, the way 3DEF is built right now is that it doesn't need any backend or any kind of computing resource. So it runs purely on the browser. So you can add any new workflow to it. And in fact, part of what we'll be, like the 3 different programming tasks we have today, which I'll be demonstrating, will kind of go over the breadth of things which we can do with the designs from 3DEF, both on and off 3DEF, like how to use the designs after. So let me run serve again. And while that thing, it should go a lot faster now because it might have done all the things earlier. Yeah, so as I was saying, going back into our slide deck. So the first programming task which we're doing is to add like a new component, which I'm just going to call the triangle trap. It's a fairly easy component. It's a rectangle with a triangular hole in the middle, and that's what it is. And the 2 big parameters which are associated with it are length and width. Now I'm going to assume that the length of this, the length and width of this one is half the times of the length and half the times of the width, and it's at the center so that it's simplified for everyone to make this design. And I'm going to show you how one can go about figuring out how to make the drawing code and how to add that new component into the 3DEF code base. Now, once this is done, so the good thing about this is once I run this view serve, right, every time you make a change onto the code base, it'll automatically compile the differences, which means that you don't need to manually compile every time you make a change, but rather it'll update it and your browser will be able to show you the latest version of it. So now that this is done, all I need to do is open it on the browser. And there you go. You have 3DEF compiling on your own computer. Now, as you know, this is version 2 of 3DEF, and it's a beta version right now. So there are a couple of things which, are slightly off and doesn't work exactly as the online version. But the reason we want everybody to contribute to this one is because we spent a lot of time over the summer refactoring the entire code to make it open source user friendly. What we realized with our older version of 3DEF was that it was very hard to add UI features and new workflows. So we used a UI framework called Vue.js to simplify the addition and like adding new workflows, adding new functionalities and components and everything, like UI components, not the components. Even that has been simplified to tell the truth. So as I said before, you can basically add like a new component. You can have different parameters for this, and then you can change the number of bends to something else and maybe something smaller. And then you can change the channel width to this. Now, if you were doing this manually, you would spend a lot of time actually modifying and messing around with the code base, with the designs and trying to make sure that everything is parametric and it's actually procedurally generated. So similarly, by double clicking on any component, I have all these same properties which come up, which let me change the different aspects of this design. And so this way you'll have complete control of how you do the design. And we also have an additional slider here called component spacing, which will basically save onto the design file so that in case you ever want to check later on to make sure that the component spacing around this component is what is correct or not, you can utilize this parameter. Similarly, you can copy, delete, move it around, and you can do a bunch of different things with it or make arrays out of it. For now, we'll be not going into any of that, but I'll be showing you all quickly how to make this quick new component in the code. So now that this is done, so because I need to make a new component, the first thing that we need to understand is how do I go about doing it, right? So the code base which we have is actually very well structured. It's easy to understand. It will take a little while, but once you know how it's arranged, it's very easy to go about it. All the UI components are inside this one. So every UI element you see on every user interface you see is inside one of these view files. So for example, it'll have all the HTML template code over here. It'll have all the what happens when you click on something, when you update a parameter, how to change everything, or when you activate, deactivate menus. It's all written over here. And similarly, it'll also have any specific styles associated with them over here. This way, if you're adding a new component over here, you don't necessarily need to know how the whole design system is built, but you just need to add your own individual component file, a view file over here, and you can extend the code and extend the UI. So that's the first step. So in order to add like a new component, right? Like what do we go about doing for that? So let's keep this over here. Now we know how to modify the UI. By modifying something over here, you can modify what the UI shows. The second part of what we need to do is we need to add we need to tell 3DOF how to understand a new thing, a new component like the triangle trap. So if you go to the library folder over here, you will basically have about like 40 different files over here, which are for each individual thing. Like the mixer, which we used earlier, like if we use a curved mixer, this one, all its properties and drawing code and everything is isolated inside that curved mixer.js. So we have some standard ways of defining these functions and everything. And by just copying that, you'll be able to do it. So you might be wondering, okay, maybe, this is complicated. I need to know how to do all these different things. How do I make something happen, right? So whenever you're approaching anything in like the UI-based design and development environment, it's very simple. You need to break down the problem you need to do. For example, if you wanted to add a new component, the first thing you want to do is you want a new button over here, right? Maybe we want it in storage, we'll call it triangle trap. And you want a new button showing up over here. So what I'm going to do is I'm just going to go back to my code, go here to my components folder, and then I'm going to go to so we'll have a component toolbar over here. I go to the component toolbar, and I'm going to say, you know what? I want to add like a new button over there. I'm going to call it triangle trap. Triangle trap, and that's basically enough for it to say that, okay, there's going to be a new component called triangle trap, and I need to figure out how to make that happen. The second thing I need to do is, but if I open this right now, you'll see the button. But when you click on it, it doesn't know what this is. It's wondering what the hell is going on here. There's like a slider over here, but it's like, yeah, this is like not anything, right? Because over here, it knows what it is. So the second thing what we need to do is we need to let it understand what the definition of triangle trap is. So in order to do that, I'm going to go here. Quickly, I'm going to go to what we call the component API. So I go to the component API. And then what I'm going to say is I'm going to add like a new item to the library called triangle trap. So I can pretty much add it anywhere I want. So what I'm going to say is, so by just repeating what is over here, by repeating the data structure, all I need to do is, there you go. I love autocomplete because it makes life so much easier. And it's saying, okay, this is triangle trap, but I don't know what triangle trap is. Because when it looks in, because there's no file, we didn't create a component definition called triangle trap. So what we're going to do now is we're going to quickly go here. Okay, just going to flag an error. So we're going to quickly go here, and I'm going to go pick the easiest thing we want to move, maybe the chamber. Yeah, So we're going to take chamber.js and we're going to copy paste that. And I'm going to call this triangle trap. Then I'm going to go in here. I'm going to say try trap. And I need to, then it's going to be like, okay, I need to modify all these things, right, to make it specific to triangle trap. And then it's going to be like, okay, I need to have some float data and all these things. But for now, it doesn't matter what it is here, right? So let's see what happens if we save this. We need to go back to this component API. You need to go back to component API to tell it, like, where is triangle trap coming from? Import triangle trap. There you go. So IntelliSense figured out where we need to get the thing from. We go back down here, it kind of knows what triangle trap is. You see the color change. So it's all nice and good, and it's recompiling everything. And it's going to basically tell us that there are no errors, and it's going to pop up something. So if we go back to our code here, you see triangle trap still here. Then you click on it, and it still doesn't give us anything. Now I'm worried. Why is that the case? Now I'm thinking, why didn't it do? It doesn't know it's supposed to put triangle trap, right? Like, it's not doing it. The reason it's not doing it is because in our UI code, when we added like a new thing, we said you need to look for a thing called triangle trap with this exact kind of text. And while we did, like, even though in component API, we said, okay, there's a triangle trap drawing definition, it's not going to know from this one. What we need to do is we need to go into the triangle trap code, and we'll be going down, and there'll be a parameter called mint. And we're going to modify this to triangle trap exactly the way we wrote it over there. So this way, now it actually knows which design it needs to pull from. Okay, reload. And there you go. It all works. So while it treats it like exactly like what a chamber is. So if I click on this, sorry, I was zoomed out. So it creates exactly a chamber, because what we did was we copied all the definition of a chamber, and it just draws like a rectangle for us, but which is the same thing as a reaction chamber. So it's basically just because we copied the drawing code and the definition for a reaction chamber, triangle trap is also basically just dropping the same thing. Now, the thing is, we need to add like a little triangle into it. Now, this is where, like the main part of like the actual hard part of like doing any kind of a 3D component design comes in. And it's also not very hard. Within an hour or so, it's very easy to add like a whole new component into the design. We have a chat question, and I'm going to go in there. Yeah, there's some folks who need to leave, and that's totally fine. Luckily enough, we'll have the recording for everybody to look at later on, and I'm always happy to chat with all of you later if you have any other questions. So now that we dropped these 3 different things, now we need to have like a little triangle hole inside it. So in order to do that, you might be wondering, oh, how do I go about doing the drawing code? Is there an easy way to learn how to do it? And that's where the fact that it's an open source software where we use other open source libraries really, really comes into play. So now this one. Yeah, this one. So that's where, like, so what we do in 3DUF is for all the drawing code, we use this library called paper.js. So paper.js is like a pretty mature drawing library, and it has a ton of references and examples for how to draw all kinds of crazy kinds of drawing. So you want to draw like something like a chain, you want to draw this or that, or rainbow. Hopefully you're not making rainbows inside 3DUF, but the point is it has ways to do all of that. Now, let's say we wanted to draw a triangle, right? Let's just there's an easy way to do it and there's a harder way to do it. I'm going to see if there's like a very quick way to like literally Google draw triangle in paper.js. And there you go. Like somebody already has an example on how to draw a triangle. So what we're going to do here is, I don't really want to copy this particular triangle code, but you know, it does a job at some level. So we're going to just basically take this entire code over here, and I'm going to copy this. And now what I'm going to do is I'm going to go into my code for like the triangle trap definition here. I'm going to go where I need to do the render 2D. So render 2D is basically the code that generates the whole thing. And as you can see over here, all we are doing is drawing a rectangle with a certain width and length and those kind of parameters. So what I'm going to do is we created the rectangle over here. So I'm going to add the triangle and I'm going to subtract it from the original rectangle. The const triangle. Okay. So apparently it's this easy to do this. So now we have this. Now I need to subtract the rectangle from the triangle. Sorry, subtract the triangle from rectangle. There you go. Let's just finish this and then let fly. Let's see what we get in here. Reload. So zoom out a little so that it's not messed up. Triangle trap. And right. Well, that did not work. Let's see. Let's go back over here. So let's say we took out this one, right? Just to check whether or not it's working correctly. So let's have this and see what happens if we pass this along. So it drew the triangle, but for some reason it did not cut it. So let's see. 4. It's here. Go back here, then reload this and see what happens. Typically, you shouldn't have too much of a hassle, but there's always a case when I might be missing something over here in terms of like, maybe I'm not using the right definition or I'm using something slightly off. So instead, we're basically just going to use this example of doing this. Actually, we can also go into paper.js and look at the documentation. That might be a better way. So I'm going to paper.js and I'm going to look at, is there a way I can create something, right? And so first I'm going to check whether or not the subtract is working correctly. So in order to do that, what I'm going to do is I'm going to take out this one. I'm going to say const rect2 is equal to angle, same point of origin, same size, radius is fine, and this one. And what I'm going to do is I'm going to say by 2 by 2. So this way, it's going to basically just cut a smaller rectangle out of the big one. I'm going to do that. If this doesn't work, I think I know why. Yeah. So the reason why this doesn't work is because I didn't realize this. Second. So if I do this, I think it'll just work. Let's see. Trap. There you go. It basically cut it off over here because it used the origin as a top left corner. But the reason why it didn't work earlier was because we didn't set it up correctly. So now let's say I had triangle over here and I said subtract triangle. So this one was, okay. I'm going to modify this slightly so it's easier to work with. There you go. So by just having this, now we have a triangle trap done. And now the best thing about this is because it's all computationally done, right? By just modifying the width and length, obviously it's not well thought out in that sense, but by just modifying the width and length, I'm able to modify this. And by modifying the corner radius, I can modify the actual corner radius of this thing. So this way, what you're able to do is, and similarly by just by pushing this along, and you notice it's slightly off because of the way we set the rotation origins. But the idea is that by just doing this, you're able to quickly figure out how you want to do the whole design. Now, for example, if I said rotation over here was 0, always set to 0, then we'll fix that little bit of rotation issues. Okay. Trap. And there you go. Now it looks clean for rotation. So what we were able to do is by quickly, in a matter of like half an hour with me explaining how to do all these things to you all, we were able to like quickly create an entire new component and add it to 3DOF. Now, if you were doing this on your own new branch over on your computer, you would make a pull request. And essentially what we ask you when you're making these pull requests is, tell us, why is this component necessary? Like, for example, this is a component that is used by many people. Like, for example, if I did a PR for this this particular component, I'd be like, no, this is not useful in any real world application. There's no papers which have used this, and there's no point in having this. But let's say you're working on your own publication, do put in saying that we are working on a manuscript right now, and we believe this is good for blah, blah, blah reasons, and then we will actually accept it. So that is task 1, making a whole new component on 3DOF. Now, I want to know if any one of you have any questions regarding doing this. Can you snap maintain aspect ratios of shape? Yes, because everything. So Prashant Vaidyanathan's question on the chat is, can we snap the width and length? Not necessarily. I don't know if you mean like, can you explain a little about what you mean by snap, Prashant?
Well, I mean, if right now you had the slider where you are
Yeah.
increasing the length, right? And then you had to increase the breadth as well. So I'm kind of curious if you can, try to maintain the aspect ratio there. So as you're increasing the length, it increases the breadth as well.
Yeah, you can do that. In our case, when we made this particular component, right, we assumed there were two independent parameters, length and width. But in some cases, as you saw, the triangle was getting cut off. So the real way of doing it would have meant that, I always had a certain aspect ratio and made sure that it was there. So it's just the drawing code. So as creative as you want your drawing code to be, the design will be that creative. The reason we want you to parameterize as much as possible, think about what your parameters are before you make the submission, is because these are standardized components which other people might use. So let's say, 2 weeks later, you want to change what the parameters are, then suddenly, like other people's designs will start breaking. And so we don't want to make that happen. So which is why we ask you to think about it a little, figure out what kind of changes you want and everything. So far, we've not had issues where we've had to change these parameters, so it broke any designs, any historical designs. But but it's something we will definitely address if we have a lot more component contributions and we're seeing this thing happening multiple times. So now that this one is done, let me take a look at what our remaining time is. So we have approximately another half an hour. Am I right?
Yeah.
Okay. So we'll go into like programming task number 2 in terms of like how do you add like a UI component? Because so far, what you all have seen so far is how easy it is to like quickly add a new component to make it work for your own special case. So I'm gonna go here. Let me share my screen and then let's go into this. So now that we did this, we added a new triangle trap, yay. Now the second task is adding a new UI feature. So in order to add a new UI feature, like how hard is it to add something to 3Dup? And that's the good thing about the version 2 of 3Dup. We've simplified how you can go about adding features, and just like how you just had to look up like paper.js code, now all you need to do is you need to look up like Beautify.js, because we use the standard UI library for doing this. So because we have a standard UI library, it's easy to just look up what UI components are available and create your own new workflow without any hassle. So in this particular programming task 2, I'll be adding a new snack bar notification onto the code, onto the design tool. What we'll do is every time the user clicks the save button, it will show a pop-up saying that, oh, downloading files now. And that's the snack bar we'll try to do. A snack bar is essentially a small window that pops up either in the bottom or the top of the screen, or maybe in the middle, based on what tool you're using, and it has some information inside it. So I'm going to stop sharing over here, and I'm going to start sharing my desktop soon. So as I mentioned earlier, we used a UI framework called Vue and Beautify for creating the entire UI. The good thing about using an existing framework and the reason why we decided to do this for 3Dup was so that it's easy to add new features. In case you're somebody who needs to add a new workflow, you can quickly just figure out what components are available in Beautify and then add those features onto it without adding any more dependencies and not breaking any CSS along the way. So what we're going to do is add a snack bar. Now, I don't know how to add a snack bar, right? Like most of you don't know how a Beautify snack bar works. So what we're going to do is we're going to go to the Beautify website. We're going to click on the search over here and I'm going to say snack bar. So I can go to the API where it gives me the details on what a snack bar is. But I'm more lazy than that. Instead, I'm going to go to the snack bar page. And I'm going to look at the different things they have over here, like the different examples they have. I'm going to pick the easiest, quickest, dirtiest example they have over here, where it is where you click on this button and it shows up a little snack bar notification. So I'm going to take this and I'm just going to literally copy paste this into my code. So I'm going to take this snack bar, model snack bar, that. And what we're going to do for now is, because we need to just show that it's going to work, I'm going to go to the manufacturing panel, because what we want to do is sorry, wrong speed off. Oops. Yeah, so basically we want this to fire when we click on this button here, 3.file.json, when we want to save this one. So this is in what we call the manufacturing export panel. So I'm going to go to my code, go to my manufacturing panel, and I'm going to look for the file which does that, right? So here's the item which does that. So instead of doing anything crazy, I'm just going to go here and I'm going to drop the thing and let the thing sort itself out. Now that the model's set, let's see if it cries about anything. Okay, I'm going to set snack bar to false, because you need to set it to false for it to work. So we'll wait for this to compile. Then when we open this, we can just go down and see if a new button got. And there you go, the button's there. We click on the button. It kind of opened it up, but it didn't know where exactly to show the snack bar. That's why it showed up over here. And that's something we can fix. But as you can see, it's super simple to actually modify stuff to make things work for our benefit. So what we're going to do now is we're going to go back over here, go back to the button manufacturing panel. We're going to look at the template and we're going to say, okay, which part of this is a snack bar, which part of this is the button. So because this is the button and this is a snack bar, I'm going to go here, take this, cut it out. And what I'm going to do is I'm going to go into the visualizer, because that's our entire grid which we show. I'm going to go down here and I'm going to drop it here. And I'm going to go in here, add another thing called snack bar. And I'll set it to false. So this way, what happens is now I'm also going to move the button because it's just easier to demonstrate. So when I put it over here, let's see where it pops up on our visualizer screen. Well, I am not sure where it's popping up for some reason. Now I'm going to take this out, and what I'm going to say is, so essentially, it's going to show whatever's inside the text. So I need to create a text option here. IWBDA box. And over here, and I'm going to set it to true. That way, it's always going to pop up wherever it is. So I go back to my main toolbar and see if it pops up anywhere. Ah, some small error. Compiling. Okay, let's check on that. And there you go. It showed us the little IWBDA rocks kind of a thing. So it was that simple to actually add it. Now, if we want to like actually bind it to like the button click, what we'd now do is we'd go in and we'd basically wire up that button click to actually fire this event. And the way we do this is by using what we call the event API. And so I'm going to go up. Where's the event API? For events. And so I can create new events over here. And each one of these events is something so that we can communicate between the different parts of the code base. So I'm going to create a new static thing called IWBDA open. Yeah, I guess that one. IWBDA open window. And what I'm going to do is I'm going to fire that event. And on firing this event, I'm going to open that. So the way I do that is I go back to my code for the manufacturing panel. So C, components, manufacturing panel. Gonna go to what happens on button click. On hitting download JSON, this is the one that fires. So I'm gonna go here and I'm gonna say event bus emit, and instead of saying snack bar or anything, we're gonna basically use the thing we called it over here. Here. And we'll basically say some text which we want to pass over here. And that's about it. So by clicking on this, the event is going to get fired. But when we actually try this now, nothing's really going to happen because we didn't actually say where do we read the event and all that. So we're going to go back to our code, go back to our visualizer and say, event back. So we're basically just going to use this little bit of code, and instead of double click, it'll be like dot IWB. We're going to say so do all that. Event bus is not defined, so we will basically import event bus over here. Sorry. Thing events flash. It's weird. Oh. There you go. So now that we have this, starts off like this. But now when we click on this one, it should set it to. Did not work. Why did it not work? So let's go back over there and see what we did on clicking the thing. Oh, testing text. We emit the thing. On visualizer, we say, I'm doing that. For some reason, the properties are not getting changed. I'm not sure why. Let's try function. I know why. Starts over there like that. Click on that. Still doesn't work. So not sure why it's not working right now, but yeah, I'm not too sure why this is not working at this point. But in principle, this is how you actually run the whole thing, to wire up different events and make everything pop up and whatnot. So I'm going to conclude this particular task for now, because at this point it's just me going into debug mode and debugging. I would like to keep the remaining 5 minutes for conversations if I want to hear more about what all of you might want to use 3.4, or if you have any ideas or comments. I want to make sure we get into that before anything else. Anyone? Any questions on what you've seen so far? Any other comments, requests? Yeah, go ahead, Prashant.
So I'm actually kind of curious about like two things. One is, so you obviously have V2 right now. So I'm actually going to circle back to workflows and trying to. So what I'm trying to understand is, let's say I have some kind of an assay that I want to test out. Yeah. And so is there kind of like, do you have examples, or do you have some kind of a workflow of how someone can start from an assay that they want to build all the way to designing something in 3DUF?
Yes. So I need to check. I'm not sure if it's because we did have a particular workshop on Microfluidics Design 101 about how to go through different papers, how to reverse engineer the designs, and how to reconstruct those designs using 3DUF as one. That was what we covered in that workshop in last year's Global Bio Summit. I'm actually going to see if maybe we might want to do a repeat of that this year again, so that people can actually dive in and learn how to do it. But that being said, if you have any requests for that slide deck, or if you need any instructions on how to go about doing that, Kenza and I are running a small community of DIY microfluidics folks, and we are always, and it's not just us, right? There are a lot of people who are experts who are happy to lend aid and help you reverse engineer and figure out how to create that entire assay design if you want.
And along those lines, it's probably a related question, but so keep in mind that I don't have much of a background in microfluidics, so I'm generally kind of curious. The constructs that you have right now in 3DUF, are they exhaustive, or have you seen some new, I guess, weird shapes propping up in literature that you had to incorporate in 3DUF?
Yeah, so that's actually one of the big criticisms most people have for 3DUF, that they don't have the one specific shape that they wanted. And by a function of sheer effort, right, like the kind of the breadth of things that go on in microfluidics, it's not possible to actually have an exhaustive list. But what we did capture in 3DUF, we have about 40 components on the whole, and we did manage to capture a good chunk of applications when it comes down to lab automation, some kind of automating your assays in the lab kind of paradigm. And also we are adding new features for like droplet-based devices for more DIY-friendly manufacturing kind of things, for CNC milling-based things, and using like conductive electrodes and everything. We are putting down all the things which we believe will have more impact specifically. But the other thing is that if you really look at the breadth of designs which people use in different devices, right? You'll always find papers coming out with like strange new geometries and designs, but for the most part, they're just optimizations of existing designs. What we've seen so far in our lab is using archetypical designs and taking a standard design and then optimizing the geometries and parameters has been super effective in getting good performances. Yes, Alexis.
Yeah, little question. How much do you guys simulate before actually making the chip? And how reliable is that?
Okay, so there's one more question. Can we? Okay, so how much do we simulate? So at one point in time, the folks in our lab used to simulate a lot, but we basically, like a huge chunk of the work in our lab is divided into either, like cell trapping and doing microscopy on it. And the second half of it is basically droplet-based operations. In the droplet-based side, one of my colleagues, Ali Lashkaripur, basically made like, created a huge data set of about like 1,200 different droplet generation scenarios. And he trained a machine learning model that will actually predict for a given kind of droplet generation rate and different kind of fluid properties and everything, what to get. So now we don't actually spend any time simulating droplet-based designs. We just directly go and say, okay, fine. If we have a new liquid where we need to learn it, we will set up a design of like 10, 20 experiments, which we'll manufacture within a day and just run them. And we'll just feed back into the machine learning model and then improve the prediction accuracy for that particular fluid or whatever variation we want. And that's actually one of the things which we want to do in the spin-off we are trying to do, where we're trying to actively build these models and make it easier so that nobody needs to really simulate the thing. Hatem had like another question for Alexis. Did I answer your question? Does that make sense?
Yes, you did. So basically what you're saying is now that you go straight from design to like characterization and then fit in your model with that, right? Yeah,
we directly do that. Of course, there are always scenarios where you might want to do some modeling, but what we've realized is that between manufacturing variations, the fluid, the fact that like any real biological fluids and all that are really hard to model in finite element solvers, and like cells have a mind of their own. It's not worth the time and effort to actually sit down and model everything very accurately in COMSOL and whatnot. Rather, you maybe do like a 1 day's worth of effort into a model just to see if it's a sanity check, and then just directly dive into like building stuff. And for the components we are actually using, we have a lot of it's not just like internal knowledge in the lab, but by actually building these machine learning models, we can make sure that these models are being shared and everything. So one of the features we'll be adding to like the 3.0 version 2 is directly having the query capabilities from those machine learning models in the future. We have a separate tool for doing that right now, but we want to integrate that into like 3.0's UI capabilities, which is one of the reasons why we went about just revamping the whole UI system for 3.0. For Hatem's question, can we build a microfluidic model of a genetic circuit to simulate its dynamics using this CAD tool? Well, this CAD tool doesn't simulate anything, but I'm curious to know what you mean by this question. You can feel free to unmute and ask, because I'm not sure I understand. I think there are 2-3 different ideas that come to my mind from this text, and I'm not sure which one is your actual question. Hatem? Hatem? Do you want to ask the question? Unmute yourself. A physical model of the genetic circuit. So are you saying that you will have like multiple genetic circuits over there, and by adding, passing the fluids back and forth between them, you want to simulate it? Is that what you're talking about?
Actually, if I can chime in on a, well, I guess one example that I can think of is, let's say you wanted to characterize a genetic circuit.
Okay.
Right. So like, let's say you have some construct and you want to run a multi-dimensional, and it has a multi-dimensional input. So, you know, I guess on the one hand, it's probably, you can probably create something straightforward where it just all the liquids flow into the cell trap. But I'm just kind of curious if, you know, there's ways of doing something that's even more complex, for instance.
Okay, so Hatem also, yes, you can. While based on what cell you want to put, that'll be a question we need to ask. Yeah, circuit on a chip, yes, you can do it. In fact, we use it for some of our own circuit on a chip simulations. So we look at, in our lab, we have a postdoc basically using 3DUF to make these devices where, you know, he can actually check how two different cell colonies with different circuits in them will interact with each other and what the dynamics of those things would be, like cell-cell communication systems. So we do that, and I'm happy to chat with you to figure out. But you know, for in his case, and we didn't publish that one particular component because he wants to hold out until his publication's out. But if you need something specific like that, I'm happy to just help, right? We don't need to be on the paper or anything. I'm happy to just build that one component for you and make sure it's going to work. Feel free to hit me up either on the Slack or later on, and we can chat about it. But yes, Prashant, in your question also, right? Like ranging from simple things, it's easy to do it on 3DUF. Once it gets complicated, 3DUF does make it easier to do it, but it does get hard to make those valve connections and everything. And in order to address that, one of the tools which we are hoping to have the first release of towards the end of the year, Neptune will have like a design language where you can literally describe all these different kinds of flow conditions and valving scenarios and everything, and generate an entire design which you can open in 3DUF and tweak around a little and manufacture it. So that's something which is within our line of sight by the end of the year. Does that answer your question, Hatem? I'm happy to chat at some point. Yes. Awesome. I think that's it from, we do have like another programming task 3, but I think we've gone over the time limit already. But I think I basically covered how to use 3DUF for either adding new components so that you can use it for your own experiments, or how to add UI if you want to add workflow. We are always happy to collaborate and help anyone who wants to write their own papers, which is why I said, you know, for fun and publications. So always happy to help. We want this platform to be used by everybody, and that's what we care about more than publications and everything. So that's what we want.
All right, thank you, Krishna. And I have to say, this is probably the first hands-on microfluidics workshop at IWBDA as well. So this is it's great, and it's also really nice to see like a pretty great workshop to see how you can use these tools real time, and how you can actually, and how a developer can also help contribute to it as well. So it's really great.